Alright, in this video we're going to use ePOP to optimize the power system of an aerial work platform. The power functions that the aerial work platform has to do is seen here, uploaded. One's a mechanical load, one's an electric load, and then there's a hydraulic load for the lift. So once we have those functions that were provided by the OEM customer, we can move on to the configuration. So here's the configuration of the powertrains. There's a lot of choices that you can make. Right now I wanted to do the legacy to reflect the legacy configuration. So you choose the power source configuration, parallel, and the different power delivery. There's lots of different ways to deliver power that all meet the same functions here. This is a more traditional way. The hydraulics provide the lift, and then a hydraulic motor provides the drive. Each and every one of these components within the configuration has a technology definition. So you can select a technology. Where you define those technologies are in the component library. So you have the ability, let's look at inverters. Every selection has a cost, a volume density, a mass density, and efficiency associated with it. You can see all the other components, in the library that need to be defined for the configuration. So we've got the legacy definition pretty good. And here we have a hybrid concept. This is a series non-plug-in with basically an E-axle and a E-pump for the lift function. So just because we have the configuration and the technology now defined, we still don't know what the size of the power source, what the optimum size of the power source is going to be. Is it going to be more engine powered or more battery powered? And since we don't know what the optimum is, ePOP solves for all the possible solutions from no battery to 100% battery BEV powered. And that's what you see here. So it's a curve. It's not a single point. It's a curve of all those different size options. This curve is total cost of ownership, which is what the customer wants to optimize for. But there are other KPIs that you could optimize: initial costs, operational costs, mass, volume. There's other KPIs that you may be more important, or you want to balance with cost and mass and volume. So the customer wasn't sure if a work site that doesn't have grid charging would have a positive total cost of ownership benefit. But here's the legacy. The legacy is here, so no battery. But actually, this part right here of the hybrid configuration, you can kind of see this local minimum. A battery (60 kilowatt hours) actually produces the lowest total cost of ownership for any of the configurations. Now this is a non-plug-in version, so even if you're not plugging it in, just the fact that it's hybrid and the efficiencies associated with that, and you can see what the actual breakdown for each component of the cost comparison, the waterfall from the legacy to the hybrid, you can understand where each cost comparison and where the cost came from. So actually this hybrid, slightly lower cost of ownership. But if you were to, let's change that hybrid to a plug-in version, you can see now that the curve has changed. You actually get an increase benefit of almost 16% reduction in cost of ownership over the legacy. in this case. So if you can plug it in at the work site, you should definitely do that for total cost of ownership reasons, because electricity in this case is cheaper than the fuel. But even if you didn't and you had a non-plug-in version of this same architecture, it would produce TCO reduction over the legacy powertrain. So this is the legacy details. This is the hybrid concept details. This is the total cost of ownership breakdown. These are the powers and sizes of each and every component, as well as the energy of the cycle. This is the solution that we will present to the customer.